tensor times gamma nu. That means, okay, the gamma 0, gamma 5 is the same as gamma 1. Or gamma 1, gamma 5 is same as gamma 0. Okay? That means the vector current is nothing but axial charge, or axial current is nothing but vector density, okay, in 1 plus 1. And this is actually nothing but the chiral-magnetic effect, okay? Or in 1 plus 1 dimensions, actually the Ohm's law is already very topological, okay? So, okay, so this is a bit small details, but anyway. So the point is that, okay, so as I said, this vector current is given by axial charge, and axial charge is of course related to the winding number of the gauge configuration, and also the axial charge is given by the density, okay, not axial density but ordinary density, okay. And this can be interpreted as the chiral magnetic effect in 3 plus 1 dimensions, okay? In 1 plus 1, so this is the relation. So this mu5, I introduced this mu5 from the relation of the anomaly relation in 1 plus 1 dimensions, but this is a little bit small details, so you don't have to care about that. But anyway, so you can derive the chiral magnetic effect very quickly in 3 plus 1 dimensions from this consideration, okay? So the 1 plus 1, the dimension reduction to a 1 plus 1 dimensional system is very, very useful when you think about the physics of a strong magnetic field, okay? And in fact, the very interesting application of this idea of the dimension reduction can be found in the argument of the magnetic catalysis. Okay, the magnetic catalysis was named by these people, the Yusenin, Miransky, and Shobkovi, in early 90s or something. So what they found was very, very interesting. That is, okay, let's consider this system, okay? Dimensionally reduced system with a very strong magnetic field, okay? So just to pick up the zero model. That is called the lowest random level approximation, A. Okay? Then the partition function for the free energy is given by the one-dimensional integration multiplied by this random degeneracy factor. Okay? So this factor comes from the transverse degeneracy. Okay? So now you forget about the transverse motion, but still you have to think about the phase space coming from transverse degrees of freedom, okay? So that is represented by this factor, plus some term that comes from the interaction, okay? If you consider the non-Bionnarazine model, for example, this lambda is nothing but the 4 Fermi coupling constant, okay? So if the 4 Fermi coupling constant is very small, then you have very large and positive coefficient in front of this m squared term, right? And that means the symmetry is restored, okay? But if this lambda is large enough, then you have some negative curvature from this integration, and this negative curvature is greater than this positive curvature, and then you can have the symmetry breaking, okay? That is the usual situation in the non-Bionnarazine model, but the situation is completely different in this dimensionally reduced system, okay? You can do this integration analytically to find this expression, okay? So this is actually already some approximated expression, but actually you can do this integration analytically and then expand that in terms of this dimensionless mass parameter, okay? So I introduced some cutoff lambda here, and then so this dimensionless mass parameter xi, okay? And then so I expand this potential in terms of this dimensionless quantity to see the curvature, okay? Then the sign of the curvature tells you whether the system is in the broken phase or symmetric phase, right? And so, as I said, okay, if lambda is small, the interaction is small, you have large positive curvature for the quadratic term. However, after the integration, you have this expression, okay, for the quadratic curvature. And that means if you go to smaller and smaller xi, this is a diverging contribution, okay? This is divergently infinitely large with negative coefficient. That means however small lambda is, it doesn't matter, okay? Eventually, this logarithmic singularity can overcome this term, okay? So the curvature is always negative. That means the symmetry is always broken, okay? So the chiral symmetry is inevitably broken if you consider 1 plus 1 dimensional system, okay? So that was a discovery by these people, and so the magnetic catalysis, so this is the magnetic catalysis, so the chiral symmetry is always broken, okay? So this is the big difference from the 3 plus 1 dimensional situation, okay? In 3 plus 1 dimensional situation, the same kind of integration is also possible with 3-dimensional momentum integration. And then you can find, so this, okay, after some calculation. Actually, this expression you can find also in the famous paper by Nambu and Nanazino, okay? But anyway, the point is the following. The point is you also find the logarithmic singularity, but that logarithmic singularity appears for the coefficient of the chaotic term here, okay? But because the dimensionality was reduced from 3 plus 1 to 1 plus 1, okay? So this, the two-dimensional stuffs, I mean the m squared is just replaced with b, okay? And then this guzai to the fourth power is replaced to guzai to the second power, okay? And in this way, you have logarithmic singularity in the quadratic term rather than chaotic term, okay? And this is how you get symmetry breaking phase in this case, okay? And interestingly, you can minimize this potential, okay? This is simply the logarithm plus quadratic, okay? But yes?
You have symmetry breaking in 1 plus 1 dimension, but there's no problem with the Mermin-Wagner theorem?
This is a very interesting question, okay? But okay, this is a dimensional reduction for fermions, charged fermions, okay? But the non-Goldstone bosons or pi zero, okay? The pi plus and pi minus, they are very massive in the presence of the magnetic field, but pi zero is still the non-Goldstone boson, okay? But the pi zero is charge neutral, so it doesn't feel anything about the presence of the magnetic field. So it still lives in 3 plus 1 dimensional world, okay? But the question is, pi zero still consists of quark and anti-quark, and because quark and anti-quark are subject to the dimensional reduction, so it may be possible even for pi zero to get dimensional reduction. And in that case, yes, the Mermin-Wagner theorem is relevant, and then the symmetry breaking is impossible. And that is actually my scenario to explain this magnetic inhibition, the lattice observation. That I wrote a paper with Yoshimasa, and yes, exactly according to that scenario. Okay, but this is technically a little bit inbound, so I will not go into the small details about this computation. But anyway, so that is very non-trivial and interesting question. Yes. So thank you very much for asking that. Okay. Yes.
If the field is weak enough, then you can use chiral conversion theory.
Yeah.
To see what's the correction to the chiral condensate. What's the prediction of KBT?
So actually, the chiral perturbation theory has the same prediction. That was done by Hispanov and what is I cannot remember the name. But anyway,
Increase the condensate.
Yes, yes. And okay, so this form is very simple, but you can find a local minimum from this very simple form of the potential. And then from the local minimum, you can get the value of the condensate, okay? And if you solve this, you can find this expression, okay? Exponential negative something over coupling constant. Okay, so this is a very non-perturbative expression, and this is reminiscent of the expression of the gap energy in the BCS theory. Okay, exactly the same structure, right? And indeed, that is so, because actually the Cooper instability is induced by the attractive interaction on top of the film sphere. And why the film sphere is needed for the superconductivity? That is low dimensionality, okay? On top of a film sphere, you effectively have a one-dimensional system, okay? And then, however small the attractive interaction is, you can have instability to have a condensate. And now, in this situation with a strong magnetic field, exactly the same thing is happening, okay? And that is a reason why you have quite a similar expression for the gap, okay? And so this system of the lambda quantized system with a strong magnetic field is, so to speak, some system that mimics the dense system on the film surface, okay? So this is also another motivation to think about the strong magnetic field effect. Okay, the finite density system is too difficult, and the sign problem is too hard. But it is possible to introduce magnetic field on the lattice. Okay, there is no sign problem. And also, this magnetic catalysis you can understand from the viewpoint of the minimization group flow. Okay, as I explained. Yesterday, maybe, yes, yes, or today? This morning, okay, this morning. So I explained how to understand the chiral symmetric breaking from the RG flow of the four Fermi interaction, okay? And I said that, so this fixed point is a critical value of the coupling constant. But so this behavior comes from the dimensionality of the coupling constant. Okay, so this coupling constant has dimension 2, and so the beta function picks up this dimensionality. However, in the system with strong magnetic field, as I said, this is a 1 + 1 dimensional system multiplied by the lambda degeneracy factor. So, okay, the dimensionality is actually reduced by 2. By the presence of this lambda degeneracy factor, okay? So this, the dimension 2 is actually taken away by the presence of this, the overall factor. And this means there is no such growing behavior here. And then, because there is no such behavior at all, of course, you have so this behavior, okay? For the effective coupling constant in the strong magnetic field, that means, okay, however small the coupling constant, the initial coupling constant is, because the beta function is negative, so this goes to infinity, okay, as you go to a softer and softer scale, okay. So this is a different but equivalent picture to understand the physics of magnetic catalysis, okay. But recently, there's some very interesting lattice results. That is, so here you see this is a behavior of the chiral condensate as a function of temperature and magnetic field. Okay, so this axis is, so this is NB, but this is actually the discrete value of the magnetic field. Okay, and so if you look at the behavior of the chiral condensate at low temperature, then this is an increasing function with increasing magnetic field. This is very consistent with the picture of the magnetic catalysis. Okay, the chiral condensate is more enhanced with stronger magnetic field. However, what is non-trivial is that, okay, usually if you have a bigger condensate, the critical temperature must be shifted up. Okay, indeed, in the BCS theory, for example, the critical temperature Tc is given by some coefficients times gap energy. Okay, so if the gap energy of the condensate increases, then naturally the Tc must increase as well. However, look at this figure. Okay, so here you have a very smooth crossover behavior, but here you have a steep drop, steep dropping behavior of the chiral condensate, leading to an even smaller crossover temperature. Okay, so this is very, very non-trivial. And so my explanation is Wagner theorem, the dimensional reduction of pi 0 that I speculated with Yoshimasa Hidaka. Okay, but anyway, so this is two advanced topics, so I will not go into this.
I have a question about this one.
Okay.
Pi 0.
Okay.
So basically, for because you got this minus sign for this pi root. Right?
Yes.
So this also exists for 0 temperature, right?
Yes.
I mean, for the vacuum
Yes.
and also for high temperature.
Yes.
So basically, if you have, so what I mean is that from Nernst result, this gives you magnetic catalysis at 0 temperature, but inverse magnetic catalysis at the high temperature,
Yes.
right?
Yes.
So, but if you, from your scenario.
Okay,
so you
the
have
singularity structure strongly depends on the temperature, and magnetic catalysis comes from the infrared singularity of fermions. And of course, the fermions do not have zero mode at finite temperature, so magnetic catalysis is significantly weakened by the temperature effect if you go to finite temperature. But this is an infrared singularity for bosons, okay? And so this infrared singularity survives even at finite temperature, and so this, the inverse effect or the inhibition effect becomes stronger and stronger if you go to higher and higher temperature. Okay, so this is why this behavior is seen at finite temperature. Okay, yes.
Can you give some comment on the alternative explanation on this phenomena suggested by the Randensburg group? They claim that's due to because C-quarter reaction and so on.
C-quarter?
Another group in Germany, there are some people claim that this phenomena is due to some they claim the due to some C-quark behavior. C.
Well, the polarization, yes, the polarization diagrams, yes.
Yeah.
Actually, there are many scenarios. Okay, that I cannot cover, but yes, in fact, there are many scenarios to try to explain this observation. And in fact, yes, such a Cork loop effect is important, and some people say that the running coupling constant is modified, and actually that is equivalent, okay, to think about the running coupling constant, okay. And if the running coupling constant is relevant or is sensitive to this magnetic field scale, then you can have some smaller coupling constant with a larger magnetic field. That means you can have more deconfining the phase, and so it's quite natural to have a smaller critical temperature. Okay, but that is actually induced by the deconfinement rather than chiral. Okay, but I think that maybe this is more relevant to the chiral physics. Because actually, so here, Massimo Beria did the same kind of calculation with heavier quarks, and then their observation was completely opposite to this, okay? So here you see, if you go to higher and higher magnetic field, the pseudo-critical temperature is raised up, okay, upward, not downward, okay? And this big difference comes from the difference in the quark mass. And so if you use lighter quark masses, then you can see that, okay? That means the chiral physics or pion dynamics must be very important. That is my opinion, okay? So.
But is there, in their simulation, the quark mass is light enough?
Well, so here, so this is a physical quark mass, I think, but so here I don't know, but the heavier the physical quark mass. So, anyway, the 1 + 1 dimensional system is very, very interesting. Also in some different contexts. That is the dense system, okay? so far, I didn't have any density at all. But, so let's introduce finite chemical potential into such a 1 plus 1 dimensional system. Okay, then what happens? What happened is very interesting. That is, this chemical potential dependence can be completely rotated away. Okay? So this is a two-dimensional Dirac-Lagrangian, okay, with two Dirac matrices. And if you change the fermion basis from this psi to rotated one by this factor, okay, and also this psi bar is also rotated. And then this chemical potential is completely cancelled by the chemical potential coming down from this exponential factor by the derivative hitting this x3. Okay. Then you have a zero density system. Okay. Then you may think that oh, then the chemical potential is completely disappeared, and so no chance to have finite density at all, because okay, if you compute the energy from this, obviously the density should be insensitive to the chemical potential, and you take the, if you take the derivative, then of course nothing remains. But that is too naive, okay? Because now let's define the chirality according to the eigenvalue of gamma 3, gamma 4. Okay, this gamma 3, gamma 4 is gamma 5 analog in 1 plus 1 dimensional system. Okay. And then you can define right-handed particles and left-handed particles. And okay, so these two species should be the momentum of these two species should be shifted in a different way. Okay, so this is nothing but a shift in momentum. Okay, if you expand this in Fourier space, of course this is a shift in momentum, and so the momentum integration is shifted downward for one species and shifted upward for different species. Okay, and then this difference produces some surface term contribution. Okay, that is nothing but anomaly. Okay, so from the anomalous contribution, you can get this mu squared term. Okay, and so in this way, in the 1 plus 1 dimensional system, the density dependence comes from the anomaly, or in other words, this term is nothing but a Wess-Witten term. Okay, or and so this is very interesting. Why? Because this is the surface integration, and so this is completely insensitive to the mass of the fermion. Okay, usually if you do the very naive computation from this, okay, you can do the computation of the free energy, and then this is the result. Okay, so on top of the zero density result, you have some density contribution, but of course the density contribution has onset. And if the chemical potential is smaller than the fermion mass, nothing should happen. However, because this density dependence is anomalous, it is insensitive to the fermion mass. Okay, this is very different situation from the normal situation. Okay, and anyway, so this 1 plus 1 dimensional lesson is very interesting. And what is interesting is this transformation. Okay. So you may think that, oh, this is just a trivial mapping to the zero density system. But because of this non-trivial rotation, the ground state structure is very non-trivial. Why? Because in the zero density system, you have chiral condensate, homogeneous chiral condensate psi by psi. So for the system after rotation, I mean the system described by this psi prime and psi bar prime, of course, you must have homogeneous chiral condensate psi bar prime and psi prime. Okay, but if this is so, if you rotate this back to the original basis, okay, then psi bar psi takes this very non-trivial functional form with cosine factor. Okay, and also you have not only psi bar psi, but also psi bar gamma 5 psi. Okay, the gamma 3, gamma 4 is, as I said, my gamma 5 in 1 plus 1 dimension. Okay, so you have this the very non-trivial structure with two condensates, and so they circle each around as a function of z. Okay, in the z direction, this forms some spiral structure. Okay, so this is spiral, or sometimes called a chiral spiral. Okay, so even though this mapping is such trivial, the consequence is very non-trivial, indicating that you must have a spiral structure for the ground state condensate. Okay, but in fact, okay, this is such simple consideration. But on the lattice, you have a problem. Okay, in 1 plus 1, this simple rotation doesn't work on the lattice. Okay, on the lattice, usually the chemical potential dependence is introduced according to the proposal by Hasenplatz and Kasch. The point is the following. Okay, the chemical potential must be introduced in a way consistent with gauge symmetry on the lattice. Otherwise, you find some very funny ultraviolet divergences depending on the chemical potential. That is quite unphysical. Okay, and then this is a conventional way to introduce a chemical potential. I mean, so this this combination, the temporal derivative and the chemical potential term. This can be expressed in this way in the continuum language, and then let's discretize this on the lattice. And then this is what you have, okay? And so in such a way, you have exponential mu and exponential minus mu here. But if you do the parallel rotation, okay? If you do this rotation, as I said, this mu dependence must be cancelled by the term coming from this D3 derivative, okay? But because mu appears in the gamma 4 part in this way, so this actually exponential mu cannot be exactly cancelled by the term coming from the the D3 derivative, okay? So this is impossible. Of course, this is a lattice artifact, and if you take a zero lattice spacing limit, of course, the cancellation works, but on the lattice with finite lattice spacing, the cancellation is incomplete. And to solve this problem, of course, you can think about a different way to introduce chemical potential. Namely, you can introduce a chemical potential in such a way that is consistent with this introduction. Okay, I mean, you can make a combination of a gamma D3 and mu. Okay, instead of this combination, you can make this combination, and then the chemical potential can be introduced by this D3 derivative hitting this here. Okay, and then this gamma 4 mu can appear after this derivative hitting on this X3. And in this way, so you can get these terms. Okay, so this may look very different from this guy, but in the continuum limit, so this guy and this guy, they are equivalent. Okay, but now you have another problem. That is, okay, if you introduce a chemical potential in this way, the fermion determinant is always real. Okay, and so at first I thought that, oh my God, I found the resolution of the sign problem, but obviously this is wrong. Okay, what happens is the following. Okay, so here you have the chemical potential dependence sign mu with difference in the 3 direction. Okay, not on the same lattice point, but with different points. Okay, in the 3 direction. So actually, for Douglas, this term changes its sign. Okay, that means for Douglas, you have opposite chemical potential. If chemical potential is introduced in this way, okay, that means this system is actually not the system with finite baryon chemical potential, but this is a system with finite isospin chemical potential. Okay, this is very surprising, right? Because in the continuum, it is obvious that okay, so this is nothing but the baryon chemical potential. But on the lattice, this turns into the isospin chemical potential. So I was really shocked. Anyway, so this shows one example of the difficulty of the sign problem, right? So sign problem is really a deep problem, very difficult. Anyway, so it is very difficult to realize this 1 plus 1 dimension